Hello everyone, welcome to Probability and Statistics for Data Science. Today we're going to learn how to evaluate classification models. First, we will define several metrics that provide complementary evaluations of classifiers. Then we will discuss discrimination and calibration. Classification models typically generate probability estimates based on input features. Discrimination measures to what extent these probability estimates are able to distinguish between the different classes. Calibration, in contrast, evaluates the probability estimates themselves. Let's get to it. We're going to talk about evaluating classification models. Classification is the problem of assigning one of several predefined classes based on input features. We're going to focus on binary classification where there are two classes, positive and negative. As a motivation, we're going to use a data set where we're trying to do diagnosis of Alzheimer's disease. Alzheimer's is a terrible neurodegenerative disease that causes between 60 and 70% of the cases of dementia. It can be diagnosed using positron emission tomography, but this is invasive and very costly. Because of this, there's considerable interest in trying to diagnose Alzheimer's using magnetic resonance imaging scans, which are non-invasive and less costly. Our goal is going to be to diagnose Alzheimer's using features extracted from this MRI, magnetic resonance imaging scans. This is an example of some slices extracted from the 3D MRI of a subject that is healthy, that does not have Alzheimer's. If you compare it to the same slices from a patient that does have Alzheimer's, I'm going to go back and forth. This is healthy, this is Alzheimer's, healthy, Alzheimer's. You will see that the brain of the Alzheimer's patient, which is basically these gray regions that you see here, the different brain regions of the patient, shrink when the patient has Alzheimer's. Because of that, a reasonable feature to use to try to classify between Alzheimer's and healthy from this data is the volume of different brain regions that must be normalized to take into account the size of the head. Here we're just going to use two volumes, the hippocampus and the entorhinal cortex, which are two brain regions commonly associated with Alzheimer's. This is a scatter plot of the hippocampus and entorhinal cortex volumes of a cohort of subjects. In black, we have indicated the subjects that have Alzheimer's, and you can see that in general, their volumes are smaller. And in grayish, whitish gray, we have represented the subjects that are healthy, which in general have larger volumes. This is the result of applying logistic regression to this problem. We already explained how to do this for this particular data set in the video on logistic regression. We have also another video on Gaussian discriminant analysis where we also derive classifiers for this problem. And these classifiers all produce probabilities. So in this case, the points at which the probabilities 1% are here, 10%, 25%, 50%. This is a linear classifier, so that's why these contour lines of estimated probabilities, where the estimated probability is constant, are lines. 75%, 90%. If we set the threshold at 0.5 to decide whether someone is diagnosed with Alzheimer's or not, then these people here are diagnosed as having Alzheimer's, and these people here are diagnosed as being healthy. And as you can see, we're making some mistakes. And we're going to see how to quantify to what extent this is a good classifier or not using several metrics essentially right now. So here is the plan. First, we're going to introduce those metrics to quantify to what extent a classifier like the one I just showed you is doing a good or a bad job. And then we're going to talk about the discrimination and calibration properties of the estimated probabilities. Okay, so evaluation metrics. How should we evaluate our classifier for diagnosing Alzheimer's? The first thing that comes to mind is set a threshold. As I said, above 0.5, we're going to say people have Alzheimer's. because the classifier estimates the probability of Alzheimer's. Below 0.5, we're going to say that people are healthy, and then we can see what fraction of the estimates are correct. This is a pretty reasonable metric. In our case, 81% of the estimates are correct. So is this it? Are we happy with this? Is the end of the story? I can stop the video here. Not quite. Why? Because people that are interested in different applications often do not necessarily care about accuracy. A doctor might ask, what is the fraction of Alzheimer's patients in my cohort that you're actually diagnosing correctly? Because I care more about that than whether you're diagnosing the normal patients correctly. And the answer is we don't know from the accuracy. That's what I mean, right? Like if I just tell you the accuracy is 81%, there's no way for you to know what is the fraction of Alzheimer's patients that we're diagnosing correctly. To drive this important point home, consider a classifier that classifies everyone as healthy, not even looking at the features. Everyone is healthy. End of story. Well, actually, that classifier on our test data set achieves an accuracy of 78.4%, which is really not too bad. Why? Because most people are healthy. 78.4% of the people are healthy. But now, if you ask this question again, what's the fraction of Alzheimer's patients diagnosed correctly? It's 0. Because Alzheimer's is never detected. We're just saying that everyone is healthy. So clearly, we need more informative metrics because in many applications, you might not only care about accuracy. In order to define those metrics, let's set up some notation. We're interested in binary classification problems. We're going to have P examples with positive labels. So in our example, these are going to be the Alzheimer's patients, which is of course not a positive outcome at all. But this is kind of standard, the standard way of going about this, where if we're trying to detect a disease, a positive label is having the disease, even though, again, it's really not positive at all. The N examples with negative labels are going to be the healthy patients in our example. I'm using examples way too much in our scenario of interest, let's say. So we can set up a confusion matrix where we're going to have we're going to be able to separate between two different ways of being right and two different ways of being wrong. What are the two different ways of being right? Well, we can have a negative data point that we are correctly identifying as negative. That's called a true negative. And we can have a positive data point that we're correctly identifying as positive. That's a true positive. And then there's also two ways in which we can be wrong. There can be a positive data point that we're identifying as negative. That's going to be a false negative. And there can be a negative data point that we're identifying as positive. That can be a false positive. In medicine, false negatives, where you miss cancer, are typically more problematic than false positives, where you tell someone that they might have cancer, but in the end, they actually don't. Realize that if we take the true positives and the false negatives, they're going to add up to the total number of positives. And if we take the true negatives and the false positives, they're going to add up to the total number of negatives. All right, with that in place, we can now define the different metrics. Accuracy, as I said before, is just the fraction of examples that are correctly classified. So we take the true negatives and the true positives, which are the two ways of being correct, and we divide by the total number of data points in our cohort or in our data set, which are the negatives plus the positives. This is what the confusion matrix looks like for our Alzheimer's example. These are the true negatives, true positives. Let's see if I get this right, because I'm always, I always get this stuff wrong. Hopefully I won't. These are false negatives, and these are false positives. I think I got it right. So now, what is the accuracy? In the accuracy, we consider all of the data points, okay? And then we want the fraction of those that correspond to, that correspond to true negatives and true positives. And that fraction is 81%, which is not bad. Now, let's introduce a metric which quantifies what we're talking about before, when you want to know what fraction of the positive examples are actually correctly classified, how many of the people that actually have Alzheimer's are identified as having Alzheimer's. This is called the true positive rate, or TPR, and also the recall, sensitivity, or hit rate of the classifier. And here what we do is we only take the positive examples, the ones that are truly positive, and we take the true positives and divide by the total number of positives. I'm not going to use truly positive again because this is highly confusing, I realize that. So we take the positives, which are these ones, the ones that have Alzheimer's, and we see how many of those do we classify correctly, how many of those are true positives. And here what we realize is that the classifier in this sense is doing pretty badly, because only 20% of the people that have Alzheimer's are classified as having Alzheimer's. Now, a complementary metric to that one is the fraction of negative examples that are incorrectly classified. That's called the false positive rate. It's the fraction of false positives among all the negative examples. So you take all the negative examples, you see how many of those, what fraction of those are false positives. You could also do the opposite, right? You could say 1 minus the false positive rate, which is the specificity or true negative rate, or selectivity, which is the true negatives divided by the total number of negatives. This expresses the same thing. If we look at our confusion matrix, now we're interested in the negatives instead of the positives, the healthy patients. We want to see among those how many of them are false positives. And there are actually very few. So the classifier is doing very well in this sense. Only 1% out of all the healthy patients are misdiagnosed as having Alzheimer's. Another very important metric is the precision, or positive predictive value. The precision tells us that if we take all of the patients or all of the data points that we have classified as positive, what fraction of those are correctly classified. So we're again taking the true positives, as we're looking at the true positive rate, but now we're not dividing by all the positives. We're actually dividing by the positive estimates, which includes the true positives and the false positives. Let's take a look at the confusion matrix, because this will make it clearer. Now we're not looking at this anymore. Instead, we're looking at the people that were classified as having Alzheimer's, and among those we want to know how many of them truly had Alzheimer's. And it turns out that the precision here is not bad. It's almost 80%, it's 78%. Among everyone that was classified as Alzheimer's, 78% of them actually have Alzheimer's. So as we have seen right now, when we compute the true positive rate and the precision, we have the same numerator, but a different denominator. Let's review that just for a moment. This is how we were computing the precision. Remember that when we were doing the true positive rate, we're doing almost the same thing, but we're looking at the fraction of the positive examples that are correctly classified as opposed to the fraction of estimated positives that are correctly classified. When two quantities share the same numerator but different denominators, it is very natural to average them using a harmonic mean. This harmonic mean is the F1 score, which captures the combined, like how well the classifier is doing in terms of TPR and precision. This combined metric for our classifier is 0.31, which is quite low because the TPR is extremely low. Now, remember that classifiers output estimated probabilities. And this holds not only for the logistic regression classifier, it holds for naive Bayes, it holds for Gaussian discriminant analysis, logistic regression, classification trees, neural networks, all the classifiers that we have talked about in different videos. The metrics that I have just defined depend on the threshold that we use to determine positive and negative estimates from these probabilities. Let's visualize that. So these are two histograms, a black one and a white one, where the black one corresponds to Alzheimer's patients, so patients that do have Alzheimer's, and the white one corresponds to healthy subjects in our dataset. What these histograms are showing us are the estimated probabilities for these two groups. So we see that the estimated probabilities for the Alzheimer's patients, thankfully, are higher. Remember that I'll tell you, the estimated probabilities are the estimated probability of having Alzheimer's. So ideally, this should be as high as possible for the Alzheimer's patients and as low as possible for the healthy patients. When we set the threshold at 0.5, what we're saying is that the people to the right of this line, the people to the right of this line are classified. Let me make a bit of a beautiful shape there. These people are going to be classified as having Alzheimer's. All of these people are going to be classified as being healthy. And you can already see that on the left, we're making quite a lot of mistakes in the sense that there's a lot of Alzheimer's patients on the left. On the right, we're actually doing pretty well, like almost everyone has Alzheimer's. Now, what happens if we push the threshold down to 0.2, for example? Now we're saying that these people have Alzheimer's and these people are healthy. And as you can see, we have really increased the number of true positives. Now there's more Alzheimer's patients that are to the right of the purple line, but we have also increased the false positives, right? So there is a trade-off there that is going to be reflected in the metrics that we defined before, as we're going to see in a moment. And finally, if I move the threshold down to 0.05, what do we see? Well, we see that now we have increased the true positives dramatically. Almost all the Alzheimer's patients are there, so it's fantastic. But also many healthy subjects are also there, are going to be misdiagnosed because only these guys here are classified as healthy. So let's quantify how these different thresholds affect the metrics that we had defined previously. This is our 0.5 threshold. Remember that basically the accuracy is pretty good. The TPR, actually maybe I'll highlight. So the accuracy is pretty good. The FPR is very good. Okay, very few false positives as we saw in the graph. The precision is reasonable, but the TPR is very bad because we're missing a lot of Alzheimer's patients, and the F1 score is not great because the TPR is so low, even though the precision is quite reasonable. So what happens when we lower the threshold? When we lower the threshold, we're really improving the TPR quite a lot. The precision goes down a bit, but the F1 score goes up because the TPR has improved so much. We see a bit, well, not a bit, like a significant increase in the false positives as we had seen before. And interestingly, the accuracy remains almost essentially the same. So depending on how much you care about false positives against true positives, you might prefer one threshold or the other. Now let's see what happens when we push the threshold all the way down to 0.05. Here maybe realize also that the true positives and the false positives have really increased when we lower the threshold, and now they're going to increase even more, quite dramatically, when the threshold is 0.05. In that case, we have an awesome TPR because we're finding all of the Alzheimer's patients, but the FPR rises to 50%. Okay, so 50% of the healthy people are misdiagnosed as having Alzheimer's. The precision goes down to just 33%. But interestingly, the F1 score is still higher than our original threshold here. The accuracy also goes down because of the fact that we have increased the false positives so much. So again, what you care about will determine, for your specific application, will determine which of these thresholds is suitable. Now let's move on to quantifying the discriminative ability of a classifier regardless of the threshold. So just looking at the probabilities. How can we do that? How can we just quantify discrimination based on the probabilities? In order to get some inspiration, let's go back to our results, and we will realize that when we go to a lower threshold, what happens is that the TPR, here is 0.19, becomes higher and higher as we let in more true positives, and the FPR also becomes higher and higher as we let in more false positives. So there is this trade-off between TPR and FPR. We want the TPR to be as high as possible and the FPR to be as low as possible. When we move the threshold, we're increasing the TPR, but we're also increasing the FPR. We can actually look at the TPR, the true positive rate, and the false positive rate for any threshold in order to evaluate the probability estimates produced by the classifier instead of the thresholded probability estimates. So here I'm showing you the false positive rate against the true positive rate for these three thresholds. So remember, this true positive and false positive rate are very low for 0.05. That corresponds to this point here. Then they are quite a bit higher, especially the TPR, for the threshold of 0.2. That's the point here. And finally, when we really lower the threshold, the TPR and the FPR both become very large, especially the TPR. These points, the remaining points on this line, are different thresholds from 0 to 1. Now, what do we want here? Well, as I said, we want a high true positive rate and we want a low false positive rate. So we want to be here ideally. A very, very good classifier would have a curve that looks like that. I forgot to say that this curve is called the receiver operating characteristic curve, which comes from the old communication literature. It's a little bit of an outdated name. So again, we want a classifier whose curve is as much in the corner as possible. Equivalently, we want a classifier that has as much area under the curve as possible. So our classifier has this area under the curve, which is equal to 0.847. It doesn't include this part. We would want a classifier that includes as much of this part as possible, so that for some thresholds it achieves a very high TPR and a very low false positive rate. This metric, which does not care about thresholds, right? It's just about the probabilities that are coming out of the classifier, is called the area under the ROC curve, or AUC, and it's used all over the place in statistics and machine learning. Now, you might find this way of quantifying discriminative ability as a little bit strange, as this area under the curve, but it turns out that the AUC has a much more intuitive interpretation, which is how I usually think about AUC. For that, in order to introduce that, I have to tell you what the concordance or C index is. So this is a threshold-free measure of discrimination performance, which is exactly what we wanted. And it's as follows. Imagine that you take your examples and you pick pairs. You pick pairs of negative examples and positive examples. And then you check the probability estimate corresponding to the negative example and the probability estimate corresponding to the positive example. If these probability estimates are very discriminative, they manage to distinguish between positive and negative examples, then a large fraction of these negative and positive examples that you pick randomly from your dataset should satisfy that the estimated probability for the positive one is higher than the estimated probability for the negative one. The fraction of negative positive examples for which that holds is the concordance or C index. And as you can see, that's a very intuitive measure of discriminative ability. Well, it turns out that the concordance or C index is exactly equal to the area under the curve. This is not immediately obvious. It's not something that you're not going to go back, look at this ROC curve and realize that that's necessarily the case. You have to do some derivations. In order to not make the video too long, I'm not going to include them here, but you have them in the solutions to one of the problems in the book for chapter 12. Okay, so now we know how to quantify the discriminative ability of a classifier, regardless of what threshold we use for its probability estimates. But is discrimination all we care about? Well, it depends on the application. Imagine that we have a classifier that assigns 0.8 probability to healthy subjects, and 0.9 probability to AD patients, to Alzheimer's patients. Now the AUC of this classifier is absolutely awesome, because imagine that you pick any pair that you pick of healthy subjects and AD patients, the estimated probability for the AD patients is always 0.9, so it's always higher than 0.8. So the AUC, the area under the curve, is actually equal to 1. This is a perfectly discriminative classifier. If you order the patients according to their estimated probabilities, you're going to get the Alzheimer's patients on one side and the healthy patients on the other. Perfect discrimination. But now what if you want to use these probabilities to take some kind of medical decision? Among the examples that we assign a probability of 0.8, if that probability really quantified the uncertainty in the classification estimate, then we would expect that 80% of those patients should have Alzheimer's. That is kind of what the classifier is telling us, right? This patient has an 80% probability of having Alzheimer's. But instead, it's actually 0. So this probability is very inaccurate. When this happens, we say that the model is uncalibrated. It has bad calibration. In order to visualize what calibration is, imagine that you take your data set and you order the patients according to their estimated probabilities. So for example, here we have all the patients whose probabilities are smaller than, their probability of Alzheimer's is smaller than 10%. How many patients in here should have Alzheimer's? So their probabilities are between 0 and 10%. So hopefully the fraction of people that have Alzheimer's is between 0 and 10%. Something that we can do is we can say, okay, it should be around 5%. If we imagine that these bins are small enough, and we can compare the empirical probability in that bin of patients, in that group of patients that has estimated probability around 5%, we can compare it to the empirical probability, we can compare it to 5%. So similarly, here are the patients whose probabilities, let me draw that a little bit better. Here are the patients whose probabilities are between 50 and 60%. We could say that, the estimated probability is around 55%. We pick the midpoint a little bit arbitrarily. Now we can compare the fraction of patients within this group who have Alzheimer's, and hopefully that will be close to 55%. If that happens for all of these groups, then the classifier will be well calibrated, because these estimated probabilities correspond to the empirical probabilities that we observe in the data once we separate the data points according to the estimated probabilities. And this is great, because then if you see that a point has a probability of 0.8, you know that 80% of such points actually correspond to an Alzheimer's patient. We can plot these estimated probabilities, which, to be clear, are just the midpoints of each of these intervals. We can plot them against the fraction of Alzheimer's patients that we see in each of these groups. And hopefully they'll be close, and they are relatively close. Okay, we see that the empirical probability tends to be a bit higher than the estimated probability. So for our example with 55%, the actual empirical probability is closer to 70%. So the estimated probability is a little bit systematically lower than the empirical probability, but the probabilities are not that bad. This estimator is quite well calibrated. Now, because I've been describing calibration in such a compelling way, you might be like, oh, but maybe I just care about calibration. Why did you tell me all of this story about the AUC and all those metrics? Like, as long as the probabilities are very accurate, what else do I want? Well, there's a catch here, because imagine that for a data set that has 21.6% of AD patients, you consider a model that just says the probability of Alzheimer's is 21.6%, which is the fraction of Alzheimer's in the population. This is a very good estimate of whether someone has Alzheimer's or not if you don't know anything else about them. But the whole point of classification is using the features that we're giving you. So here you wouldn't even look at the MRI. You would be like, oh, the probability is 21.6%. Let's take a look at how well calibrated this classifier is. So there's only one bin. Think about it, and I recommend that you stop the video and maybe think about why this is the case. Because how are we ordering the patients? According to their estimated probabilities. But now they all have the same probability estimate. So in our graph before, there would just be one bar for all the healthy patients and another bar for all the Alzheimer's patients. Within that bin, how many of those patients, what's the fraction of those patients that have Alzheimer's? It's exactly 21.6%. So this classifier has perfect calibration. Is it a good classifier? Maybe stop the video, think about it. It's a horrible classifier. I just told you the classifier is not even looking at the features. It's completely non-discriminative. So calibration is important in the sense that you want the probabilities to be meaningful, but that the probabilities being meaningful does not mean that they are going to be discriminative and enable you to separate the data points between the classes. So you still need something like AUC to tell you how discriminative the classifier is. It turns out that there's a metric that combines calibration and discrimination, and this is often used in forecasting applications where you do care about the probability, but of course you also care about being discriminative. So given a data set where you have these features x1, x2 to xn, and the corresponding labels that indicate the class y1, y2 to yn, the Brier score is the difference between the true label and the estimated probability. It's the squared difference averaged over the whole data set. It turns out that this evaluates both discrimination and calibration at the same time. This is not immediately obvious. There's another exercise in the book in chapter 12 that shows this, and you have the whole derivation in the solutions. If I included in the video, this video would just be way too long. The classifier that is perfectly discriminative, the one that was assigning 0.8 to all the healthy patients and 0.9 to all the Alzheimer's patient, which was very uncalibrated because these probabilities were completely wrong, has a Brier score of 0.504. The classifier that was perfectly calibrated but not using the features, just giving like a fraction of a probability of 78.1% to all of to everyone, without caring about the features, and was hence completely undiscriminative. That classifier has a Brier score of 0.169, and our classifier has a Brier score of 0.131 because it is reasonably discriminative. Its AUC is not bad. I forgot to tell you what the AUC was. I'm going to go back and tell you in a moment. And it was quite well calibrated. Like if you remember looking at the reliability diagram, which is this curve that compares empirical probabilities to the probabilities within the bins, it was not bad. Let me go back and tell you what the AUC was, because I can't believe I actually forgot to tell you the value, and I'm pretty sure that it's on the graph. Yeah, so the AUC is 0.847, which is considered a good AUC. So here logistic regression is doing a pretty good job discriminating between Alzheimer's and healthy patients. And I don't know why I was describing the curve to you when I could have just shown you. This is the reliability diagram that compares the estimated probabilities to the empirical probabilities once we have separated according to those estimated probabilities. And it's pretty good. The points are not that far from the diagonal where the empirical probability corresponds to the estimated probability. And that's it. So what have we learned? We have learned that there's many ways of evaluating binary classification models, and the way you use will depend on what you care about in your application. We have defined accuracy, true positive rate, false positive rate, precision, F1 score, which depend on the threshold that you use to threshold the probability estimate coming out of the classifier. We have defined AUC or concordance that captures the discriminative ability of the probability estimates produced by the classifier. And we have explained how to measure the calibration of the classifier, which tells you how good these probability estimates are in terms of just whether they are accurate probability estimates. And finally, we introduced the Brier score, which allows you to have a certain trade-off between to basically measure the discriminative and the calibration abilities of the classifier at the same time. And that's it. That's all I got. Thank you very much.